perfect. All right, so tonight we're gonna go over the basics of astrophotography. The idea is to kind of go over all the various pieces of equipment, at least the most crucial ones, give you some insight into how they work, how you might select them, how you might use them, and astrophotography is a big topic. It's impossible that we're going to be able to cover everything here in 2 hours, hour and a half. So the idea is to have some subsequent meetings where we can discuss more. And again, it also on Saturday we have our Geneva night. So I plan to show up there early, and I'm trying to recruit more people to come and join me early. And so for you, those of you that may have some questions or want to discuss something in person, I think Saturday will be a great opportunity to do so. And again, if you have any questions throughout tonight, use the raise hand feature. I might not see it. So, if you're waiting for a while, feel free to just speak up and interrupt me. All right. So the goals for tonight are to demystify astrophotography and some of the various terms that you may be hearing around, right? There's a lot of words like HFR, full width of maximum, offsets, gains, and sometimes that can it can be too much, and you can get bogged down, especially if you're starting. So the idea is to give you a clue of what that all means, provides a background on the various settings on the equipment that you might use, and a computer setup such as a ASIA or Nina or something else, or any other equipment that you may need to control it. If we have times, I'll try to go over the basics of it tonight, but I am planning a dedicated class on that, for example, on Nina and how you might set up a computer to run your setup with it. So a quick summary of why you do astrophotography, how you do it, and this is making it sound super easy, right? You point your camera at a region of interest in the sky. You make sure that your camera is moving at the same rate as the stars. You take lots of pictures, hundreds of pictures. You calibrate these pictures with dark frames and flat frames, and then you stack them and you get one final pretty picture. So again, it's making it sound really easy, but in essence, that's essentially what you have to do, right? There are more steps involved, obviously, in each one of these points, and that's kind of what we are going to discuss tonight. All right. So let's start with equipment. So I have a list. I made a list here of all the equipment, and I broke it down in 3 categories, right? I have necessary, something you absolutely need, or you're not going to be able to do anything. Essential, not necessary, but it'll be a lot easier if you have this. And, argument could be made, some of these should be in the necessary or vice versa. But then there's the optional things you absolutely do not need. They do make life a little bit nicer, but you 100% can do everything without them. So on the necessary part, and you see I highlighted 3 here in red, right? You need a mount, you need some sort of lens or telescope in a camera, right? You absolutely need those 3 things, or you're not going to be able to take pictures of the sky. Now, as far as mounts, you can use a tripod, and I've seen that done. It's a lot more work to be manually moving your camera. Your stack might not be as good, but theoretically you could just do a tripod if that's all you have right now in a camera. There are lots of YouTube videos covering that, but I'm going to assume we at least going to have a mount here. Lens and telescope. You need to be zoom in that portion of the sky that you're interested in, and obviously a camera, whether it's a DSLR or a mirrorless camera or a astrophotography camera, you will need something to take pictures, right? Notice I put the computer here in the essential. If you have a DSLR, you absolutely do not need a computer. You can take a simple intervalometer, like a little controller, or even program it in the camera itself to take pictures, of whatever exposures you want. And you go from there. If you're using an Astro camera, you will need some computer, something to control the camera. whether it's a laptop or something like an ASI Air or a mini computer that's mounted on your telescope. I added flat panels here under necessary because you want to calibrate your images, right? There's a lot of discussion and I think different opinions into what you need. But I think at the very least, you need flats, right? And flat panel here can be anything from like a dedicated drawing panel, something automated, or just a white piece of cloth that you put over your telescope and you point to the sky early in the morning and use that as sky flats, right? But you want some sort of flat images, and I'll cover these here in a little bit, because they will make your pictures look a lot nicer. They'll correct for dust, vignetting, and some other effects, and it'll be a huge improvement to your images if you're not using these already. And then I added a heater under necessary because we're in Florida, and most of our nights the humidity it's close to, if not 100%. So depending on the telescope you're using, you more than likely will get dew on your lens. So you want a heater to control that. All right, on the essential, again, the computer, which like I mentioned before, if you use an Astro camera, this moves over here to the necessary. Focuser, right? You don't, let's say, need an automatic focuser, right? You can manually focus a couple times throughout the night. But your focus will change throughout the night, whether it's because the temperature is dropping, the ambient temperature, there are some thin clouds rolling in, the variety of reasons. Humidity here in Florida will cause that to change as well. So it'll make your life much easier if you have a focuser installed on your telescope that can do that for you, rather than checking it yourself. A guiding system, depending on the mount that you have or the length of exposures, and I'll go over this part too more in detail, you will need to guide, right? So that the mount's tracking your object in the sky, but it's not going to be perfect, right? The mount, the gears aren't perfect. The atmosphere is causing some drift. The polar alignment is causing some errors. So you need a system that's telling your mount when it's drifting away from the target and can issue corrections quickly, right? We're talking like every second, every 2 seconds or so. Right, and every mount's different. Some mounts can go unguided for 3 minutes, 1 minute, 5 minutes, depending on how much they are. Or some mounts, like harmonic mounts, just cannot go unguided for even 10 seconds. So that'll be up to you, whether you think you need it or not. But more than likely, most systems you'll need to guide. Filters and drawers. Whether you're shooting with a color camera or a mono camera, right, if you're shooting with a mono camera, you 100% need filters. If you're shooting with a color camera, you may want to do some filters just to fight the light pollution, especially near Orlando. And power management, right? These equipment here, they have a lot of cables. Everything needs to be connected to a computer. So having some sort of hub where you can connect everything will make your life a lot easier. And then here under optional, right, things you absolutely do not need, but they're nice to have, a filter wheel, so you don't have to change filters manually throughout the night if you want to use more than one filter in one night. An electronic rotator if you want to change your framing automatically without having to touch your telescope, which is nice if you're doing 2 or 3 targets in one night, so you don't have to get up in the middle of the night or just decide to live with one framing. An automated flat panel, so your flats are taken care of automatically, and a weather station to keep you aware of what's going on. Again, not needed, and this optional list can go on and on and on, but just to give you an idea of some additional components that are there so far. Any questions right now? All right, great. So what I'll do now is I'll go over a couple of these pieces of gear on the list here. And I'll try to go in order here from the necessary through most of the essential ones. All right. So let's start with the mount, right? And notice I put the mount before lens and telescope. Um, the mount, you'll hear oftentimes that it's the most important piece of equipment, right? Because if you don't have a way to track your object and point your camera and lens to the sky, you're not going to be able to take pictures, right? So the purpose of the mount is that it's holding your camera and your telescope and everything else, and it's going to point to the region of interest that you want, right? And it's going to track that object throughout the night. So you have a couple options in mounts. You can do a manual mount where you have to find the object yourself, right? So either by star hopping or it's just bright enough that you can just see where it is right away. Or you can have a go-to mount where you basically use a computer and you tell it what object you want, and it will automatically point to that object and track it throughout the night. And then you have different types of mounts. So you have something an alt-az mount or an altitude azimuth mount, equatorial mounts, or a star tracker. And within these, there are different categories, right? You got like fork mounts and some other types. I'm just gonna quickly cover what these three types are and what coordinate systems they're using, right? Because that's really what the difference is here. So an alt-az mount or an altitude azimuth mount, these are mainly used for visual observing, and what they're doing is they track the altitude and the azimuth of an object, right? So think of the azimuth as the angle from the north, right? So it's giving you basically the cardinal direction, right? So azimuth of 0 is north, 90 degrees is east, 180 would be south, 270 west, right? So 360 or 0 again north. And then the altitude, it's how high it is in the sky, right? So if you move your arms up and down, that angle is the altitude angle that we're doing here. And so if you're tracking an object, the altitude and the azimuth of the object will change throughout the night, right? Because it's moving higher in the sky and then back low, and it's moving from east to west. So its coordinates and altitude and azimuth are changing. And that's what this mount is tracking. But the reason we don't want to use this type of mount for astrophotography is because it doesn't rotate with the object, right? So if you're taking a long exposure, the object is rotating in the sky as well. So, but this mount won't be able to track that. So you wouldn't be able to do very long exposures at all, right? So if you think of a Ferris wheel and you have a camera mounted on a tripod, without that camera moving, you're able to keep the Ferris wheel in the center of view of the camera. But the Ferris wheel cars are going to be rotating relative to your frame, right? So it's always going to be a blurry image if you're taking long exposure. So that's kind of the same idea here. So to get around this, we use a equatorial mount that tracks the right ascension and declination. So before I talk about that mount, let's talk about what right ascension and declination is, because I know that can get confusing, right? All right, so let's look at this image, right? So we have the Earth here, and it's length, right? It's rotating around its axis, which is at 23.4 degrees, and it's rotating around the sun. So now if we think of a sphere growing away from the Earth, right? So it's an imaginary, infinitely large sphere that's centered around Earth. And every star, every object out in the sky that we can think of is projected onto the sphere. And they are not moving, right, relative to the Earth. I mean, they are, but it's so slow that for all intents and purposes, they're not moving. So every object is fixed on the sphere. So as we're rotating around the sun, right, we're rotating throughout the day, we are seeing different objects on the sphere, right? And whether you're on the northern hemisphere or southern hemisphere, right? And that kind of explains why you see different constellations in the north or in the south, and why we see different constellations throughout the seasons, right? All right, so we have that sphere. Now think of our equator line, right? This little line right here. And if you project that equator onto this imaginary sphere, or we're going to call that the celestial equator. So right ascension, it's telling you where along the celestial equator the object is, right? So again, the objects on the sphere are not moving. So right ascension, inclination are essentially, if you think of a graph like the XY, like where on that graph, where in the sphere those objects are, right? So right ascension is going around basically the diameter of the sphere on the celestial equator, telling you where the objects are. And then declination, it's the distance north or south from this sphere, from this equator on the sphere where they are, right? So where zero, a declination of 0 is right on the celestial equator. Declination of 90, plus 90 would be the north celestial pole. Minus 90 would be the southern celestial pole, right? So again, right ascension is where on the celestial equator we are, and that's given in units of time, right? In 24 hours, more or less. And then declination is in degrees, is where along north or south we are from that line. So you can think of right ascension almost like east and west, and declination almost like north and south. Questions so far on right ascension, declination? Okay. And then another term that we should be aware of when using equatorial mounts and when tracking any object really is the local sidereal time, right? So one day or a solar day has 24 hours, so we're used to, but a sidereal day has 23 hours, 56 minutes, and 4.1 seconds, actually, right? And that's the actual duration of Earth's rotation, right? Goes around once. And it's also the reason why every 4 years we have a leap year, right? Because we gotta account for this difference between 24 hours and 23 hours, 56 minutes, 4.1 seconds. Otherwise, our seasons over time will just be out of whack and not when we expect them to be. So sidereal day, right, is if you divide a day in this amount of time. Another term to be aware of is Greenwich, right? You'll hear a lot of Greenwich sidereal time or Greenwich mean time, right? Greenwich, England, for historical reasons, because the English dominated the world with their navy. But specifically, Greenwich has a longitude, right, of 0 degrees. So longitude, right, going from east to west. We define Greenwich as a longitude of 0 degrees. So our local sidereal time will be the sidereal time in Greenwich, so the Greenwich sidereal time, plus your local longitude divided by 15 degrees. Right? So another way, so if we know what our local sidereal time is, another way to think of it is that the right ascension tells you the local sidereal time at which that object will cross the meridian, right? Well, the meridian, if you think of an imaginary line between the north horizon and the south horizon, right? So that's the local sidereal time at which the object would cross the meridian. And it is at that point that the object's at the highest point in the sky, all right? So for example, and again, right ascension never changes for an object. It's always that, right? Because it's really basically the grid point of where in the sphere it is. So that will never change, even if it's moving throughout the night, right? Because it's us that are moving on Earth, not the object on the celestial sphere. The right ascension is never changing, unlike the altitude and azimuth. So we know that Orion has a right ascension of 5 hours, 50 minutes, 59 seconds. We know that it will cross the meridian when our local sidereal time is 5 hours, 50 minutes, 59 seconds, right? With that for today is really close to 1 a.m. And again, because the sidereal day and the solar day differ, every day, the time at which it crosses the meridian changes, right? Ever so slightly. All right, so now let's go back to mounts. So an equatorial mount, they point in RA and declination, and they can point to the RA and declination of an object and keep track of this, right? And again, these will drift due to mechanical imperfections from the mount, not because the object itself is moving. So with an equatorial mount, you have to align the RA axis of the mount with the north celestial pole, right? And that's what we call polar alignment, as I'm sure everyone has heard of that, right? Unlike the Aldas mount, which all you do is you star align, right? You find 1 to 3 stars and you make sure that they're in the center of view of either your camera or your lens, your eyepiece, and that's how you align that mount. Right here, we're making sure that the RA axis is perfectly, or as perfect as you can, align with the north celestial pole to reduce any drift. And these types of mounts do require counterweights. There are some new variations, these harmonic strain mounts, right, such as the CWAM series or the Skywatcher Wave series, that they don't require counterweights or really require them when you're near the payload capacity of the mount, more so that it doesn't tip over. These also need to perform a meridian flip, right? So when your object crosses the meridian, in your telescope and everything will be basically pointing to the zenith, and unless you rotate it to the other side, it's going to keep going and eventually crash into your mount or your tripod, right? So when the object crosses the meridian, you need to perform a meridian flip. Again, if you're using a computer, it'll do it automatically. And these mounts account for field rotation, right? Which is exactly what we want for astrophotography. So your camera is rotating at the same rate as the object, so you can take long exposures and not worry about them not coming up. All right, questions so far on equatorial mounts or RA and the coordinates or anything? All right. And lastly, star trackers, right? These are small mounts, and they're essentially equatorial mounts, small equatorial mounts that only track in right ascension. So they don't account for any drift and declination. And most of them are manual, where you have to point in RA and declination manually. But then they will only move in right ascension, even if they're a go-to, right? These are typically used for small setups. So you have a camera with a small lens or a small telescope, right, to more or less 200 millimeters of focal length. And it's because that large field of view that you don't have to worry about really any drift and declination coming up in your pictures. But for these, polar alignment is very crucial, especially the more weight you're putting on these mounts. So yeah, I already mentioned that you don't have to worry about that. All right, so some pictures, right? So here's the Aldas mount. So again, it's moving in altitude, right? So up and down the telescope here, we think it will move like this. And from this base here, it will move sideways like that for the azimuth. Here's the equatorial mount, right? So it's moving, this part here is moving in right ascension this way, and the base here it's moving in declination. And this is a harmonic mount, which is basically the same as the equatorial mount. You'll just notice that it doesn't need counterweights. And here's a star tracker. Again, it's essentially a small equatorial mount that it's only moving in the RA direction, right? The declination base here is fixed. All right, so that's it for mounts, right? So you essentially, if you learn anything about this, is that you want an equatorial mount. If you want a lightweight mount, and willing to pay a little bit more, get a harmonic mount. If you're okay with moving a big mount out every day to a yard, or you think you have a permanent setup, a traditional equatorial mount with some weights is great. Or if you just want a camera with a small lens or small telescope, a star tracker will probably suffice. Um, and then as far as polar alignment, you'll notice the equatorial mount here has a small scope where you can use to find Polaris and polar align with. Or if you don't want to use the scope, or you have a harmonic mount that doesn't have any of these, once you have a computer, they will have polar alignment routines where they will point the telescope at 3 different locations in the sky and tell you how far away you are from the North Celestial Pole, and they will tell you how many degrees to move the mount um, in both azimuth and altitude, and it will be constantly taking pictures telling you when you're polar aligned. All right, so now that we know what the mount is, the next thing we do to take astro pictures is a telescope. And the first thing I'll say is that you don't really need a telescope, right? You can use a camera lens as well. Especially if you have a background in photography and you have many different lenses, or just get a great deal on the lens, and you're planning on using a DSLR mirrorless camera, they're great. One thing to keep in mind too with the lenses, that the connections, they differ by manufacturer, right? So if you have like a Canon lens, you typically only can use a Canon camera with it. Or if you want to use an Astro camera, you got to do some research to see what connection you might need to connect it there. So the connections differ by manufacturer, and it would over time, right? So Canon, for the longest time, they had these EF lenses, and they have one type of connection, and now their newer lenses are these RF lenses that have a different type of connection, right? So again, camera lenses are great, especially if you want to do like some Milky Way photography. But if you want some more magnification, it's probably cheaper to go with a telescope. Even I think a small telescope might be cheaper than some camera lenses, at least to get the quality one. And telescopes too. Remember that they're made specifically to look at it and photograph the sky. Camera lenses are made for really any other different type of photography. So while they might work well, they're not optimized to focus on stars. So telescopes, they come in many different flavors, many different types of telescopes. Briefly gonna mention, the 3, I think, most popular ones for astrophotography would be a refractor, which is the simplest type that you can think of, Schmidt-Cassegrain, in a Newtonian. Both of these two here being classified as reflectors, because they have a mirror that reflects the light onto your eyepiece or your camera lens. And I'll briefly touch upon refractors and reflectors. And some words that you might hear around, some terms to classify telescopes. One would be focal length, right? So how far it can zoom in. A small telescope might have a focal length of like 250 millimeters, 300 millimeters. And you can get a large telescope, right? That'll get you to 2,000 to 2,300 millimeters, right? That's where you're going from like a refractor to then a Newtonian or an SET to really get that much zoom. The aperture, another term you'll hear, is the diameter of the main lens, of the front lens, or the main mirror on the telescope. And then the F ratio, which is really the ratio of the focal length divided by the aperture. So that will give you an F ratio, right? So low numbers, right, in the 2s, people call them as fast telescopes. And the one thing I'll say about that is that it's hard, I think, to compare like F ratios between 2 telescopes when they have different apertures and focal length. I personally, when I'm comparing F ratio, I prefer that to do that within the same telescope, right? So like if I have an SET, for example, where I can change the focal length on it anywhere from its native focal length, which is 2,350 millimeters, to 500 millimeters. with different attachments, right? So then my focal ratio is changing, my F ratio, right? By my aperture staying the same. So it's such a large diameter that I can the lower the F ratio, the more light I can gather. Um, but then it's kind of an apples to oranges comparison if I'm comparing the F ratio of that telescope to like a refractor that has a much smaller aperture, because even though the SET may have a higher F ratio, still a larger aperture, still going to collect, I think, more light. So when you're looking at F ratios, try to look within comparable telescopes. Don't necessarily compare it from, one SET to like a red cat refractor. So speaking of refractors, right? Like I said before, they're the simplest type of telescope. Um, they have an objective lens here at the front where they collect the light and will then focus it onto your eyepiece, right? And then more sophisticated ones and more expensive ones will have more lenses inside the telescope tube, right? To correct the light for different chromatic aberrations, to flatten the image, and so on. So the very popular Red Cat 51, right, has a focal length 250 millimeters, and it's a Patsville design. I believe it has 4 or 5 different lenses on the inside and gives you a flat image. Right, so or you can get a bigger refractor for almost the same amount of money that only has 2 or 3 lenses, right? So the more lenses, the more expensive it is. So refractors, typically you'll see them in the range of 200 to 800 millimeters, right? Larger focal lengths, they start becoming very, very expensive and very heavy, right? So I'd say you want a refractor that can do 1500 millimeters. You might be paying $20,000 for that very large telescope, versus paying $2,000 for an SCT that's going to be significantly smaller. So refractors are great when you're in this low to medium focal length range. The advantage is they're very simple to use, right? You don't have to worry about collimation. They'll adjust the acclimate to temperature much quicker. So if you're getting started or you just want to set up that it's hassle free, refractor is definitely the way to go. All right, yeah. So another thing is they'll naturally focus the light onto a curved surface, not a flat one, right? So since camera sensors are flat or curved, you have to correct that curvature to get optimal images, right? Or you might get like weird aberrations in the corners. So that's where a pathful design like the Red Cat will have this flattener already inside the tube, right? Part of it. Or you might, some older designs, you might need to get a flattener that you screw on the back of the telescope separately. So when you hear people saying that you need a flattener with the telescope, that's what they're talking about, right? So typically, if you get a refractor that only has 2 or 3 lenses, you might have to buy a flattener separately. You also have reducers that you can attach to the back that then reduce the focal length on the telescope and give you a greater field of view. And some flatteners, then that you have some flatteners that also act as reducers. Right. Then you can have a reflector type telescope. Here I'm showing a Newtonian. So the way these works, these reflectors, right? You have your light, they'll enter the tube, they'll hit this primary mirror here, then they'll bounce the light back onto the secondary mirror, they'll focus it here, and this mirror will then reflect the light onto your eyepiece or a camera back here, right? So the advantage of this complication is that now you can see the light path is you're increasing the light path, not the light path is greater than the length of the telescope, right? Because you're going here, then you're bouncing back here and coming here. So that increase in the light path is what's giving you that greater focal length. So you can have a much greater focal length without having such a big monstrosity as you need if you were to stick with a refractor, which is just straight up. But then it has some additional complications, right? Because it's so large. They take longer to acclimate, where you can, the temperature on the outside of the telescope compared to the inside can give you some weird effects on your stars. You have to worry about collimation, which is where you need to ensure that the central mirror, the small mirror here, is perfectly aligned to the center of this back mirror here. Otherwise, you're gonna get weird things on your stars. So overall, they're a little bit more tricky to use, right? And an SCT is very similar to this, except that instead of bending the light at an angle back to here, it will bend the light straight back, and the primary mirror will actually have a cutout in the center for the light to go through. But again, these are more complicated setups. They require more strict guiding. You have to wear collimation. But if you are after focal length, then this is, I think, the way to go. Unless you want to get a huge mount and pay an absorbent amount of money for a good large refractor. All right, so that is it on telescopes. I'm going to move on to cameras. Unless any questions so far? Great. All right, so now cameras. So you can use either a DSLR or mirrorless camera, right? Or you can have a dedicated astrophotography camera. Most of my experiences with astrophotography camera, so I'm not going to touch more on mirrorless cameras or DSLRs. But I started, with what I had, which was a mirrorless camera when I started astrophotography. Again, as long as you have the right connector, I even connected it to my small refractor, the Red Cat 51, and I was taking great images with that one. But there are a couple of advantages to having a dedicated astrophotography camera, which is why I quickly move on to that. Right. So the main one is you can cool up the sensor up to 40 degrees below ambient, right? So 40 degrees Celsius, right? So that means that here in Florida, I can cool the sensor typically to around 14 degrees Fahrenheit is the temperature keep the sensor at, right? So that's minus 10 degrees Celsius. So that's nice because then that reduces the thermal noise in your images. So you'll get cleaner images because that sensor is cool. Even as you're taking more images, it's still at the same temperature. Right, it doesn't have a mechanical shutter. So as you're taking the picture, it's not vibrating or anything. And the nice thing about it too, because you can control the temperature of the sensor, you can take your set of darks at any point especially during the day to calibrate your images because you're controlling that, right? What I found the most frustrating when I was using the mirrorless camera is that I would have to then, before the sun came up, I would typically, because you want the sensor to be around the same temperature, I would spend 1 to 2 hours taking darks, where that was time I could be using to take more images. And you have to take your darks then after every imaging session because your sensor is going to be a different temperature. It's going to warm up throughout the night, which is, again, with the Astro camera, you set the temperature and you forget about it. You take darks and you can use them up, for a year if you want. You don't have to worry about it again. So again, the Astro camera is specifically designed for repeated long exposures. They have lower noise levels. They also specifically designed to be used with telescopes, so all the adapters and right connectors already included typically with your camera, and all your components are made to work with it. But the main downside, right, is that they have no screen and they require a separate computer to take and view your images, right? Where the DSLR, you don't need a computer at all, right? You can just use your screen to set your images, all your settings, and then use an intervalometer, right? A small control to set up your sequence, and then that's it. So if you're using an Astro camera, it does bring some additional complications. Now for the rest of my here presentation on cameras, I'm mostly going to be focusing on Astro cameras. So again, just like telescopes, they come in multiple flavors, right? And there are different manufacturers, right? CWO, Player One. I can't think of any other brand right now, but there are many different brands, right? But the sensors they use, they all use the same sensors, right? So where they're different is how they packaging that sensor to try to squeeze the most performance out of it, right? So the sensors will have different sizes, where you can have anywhere from a full frame or APS-C to the square 1-inch sensor. Another popular one is this 11 by 6 millimeter, the 585 camera. So again, most of them are Sony sensors. Most cameras they all use the same sensors. It's just how they package it. Every manufacturer will package it and give you slightly different performance on the same sensors, right? But the sensor size, even if you take two different sensors on the same camera, on the same telescope, they will give you different apparent focal lengths, right? They're not increasing the focal length, they're just cropping the images. So don't expect like an APS-C on a red cat to give you the same image as this type of sensor on a red cat, right? And that's what I'm giving here, right? So this is from a telescope simulator on telescopios.com. So both of these images, right, assume the 250 millimeter focal length of the red cat, and then I have two different camera sensors, right? So that APS-C sensor, or that 1 by 1.2 inch sensor, which is that 585 sensor that's really popular. So you can see here how that APS-C sensor is bigger, so it's capturing a bigger field of view in the available aperture that you have from the telescope. But if you have a smaller sensor, right, obviously all it's doing, it's cropping your image, but showing you that image on your full screen still. So the object appears to be bigger, even though you're on the same focal length as both of these. So I could take this sensor, right, and crop it to this same field of view here. The only difference, right, is that it's not going to look as good as if it's the sensor cropping it. Right, it'll be less noisier. So you can, if you're in the market for a camera and a telescope, you can play around on a site like Telescopios or Stellarium, right, and put in your different sensor sizes and telescope size, and see what gives you a field of view that you like for a lot of the targets that you're after. So right now I own both these cameras, so every time I'm going after a target, I'll play around and see which camera I want to use with which telescope to give me a good framing. All right, and then the other choice you got when you're going to pick a camera is if you want a color camera or a black and white camera, right? So by design, all the sensors are mono sensors, monochromatic, right, or black and white. So even a color camera and a mono camera, right? They were both, let's say, use a 585 sensor. It's the same sensor on both. The difference is the color camera will have a grid of red, green, and blue filters, like little filters. That's called a Bayer matrix that's placed over each individual pixel of the camera. And so it's that set of filters that give you a color image, right? And the most common pattern is this RGB pattern. So you get one red pixel, two green pixels, and one blue pixel. So the downside of these color cameras is that each pixel only gets about a third of the light, right? And they're less sensitive than the mono cameras because you have this Bayer matrix in front of it. And in the mono cameras, you get the entire sensor, 100% of your pixels are collecting all the signal all the time. So mono cameras are a bit more efficient, even though you have to change filters, but you get more pixels collecting light for that filter, right? So, example, if you're shooting narrowband, where you're really only focusing on a very small bandwidth of the light spectrum, let's say your hydrogen filter in your one-shot camera, only the red pixels, right, are the only ones that are able to gather any light at all when you have an HA filter in front of it. With your mono camera, if you put an HA filter, still 100% of your pixels are going to collect more signal. So you can see how, if you have 10 hours of integration of one image with a narrowband with a mono camera compared to 10 hours of integration with a OSC camera, the mono image is going to look better, right? Because you gather more light with your pixels. But again, they have it's a more complicated setup because now you need to buy filters. You need to get a filter drawer or a filter wheel. So it adds up in price quickly. But it also cuts down on the amount of time you need on a target. But an OSC will give you still very, very good results, and it's a very simple setup. So just to harp a little bit more on the efficiency, right? So each camera will have something called the quantum efficiency, right? So each sensor will have its different quantum efficiency. So you can go to your camera manufacturer's website, and they'll typically post this quantum efficiency. And that's the percentage of the incoming photons that the sensor can convert to electrons, right? So it gives you a plot of wavelength versus the efficiency, right? So for example, it's telling you that at around 550 nanometers, it can capture about 91% of, it has an efficiency of 91%, right? So it's only losing about 9% of all the incoming photons at this specific wavelength. So what I did here is I put the quantum efficiency of the sensor, the Sony IMX571, which is an APS-C sensor. This black line is the quantum efficiency when it's just the mono sensor, right? So no Bayer matrix. And then the color lines are the quantum efficiencies for each color when you have the OSC, the Bayer matrix, right? So again, if you have the red sensor here, right, at the wavelength that you're getting from the red filters, you can see that your efficiency is about 15% or so lower than on the mono sensor, right? So if I were to add the sensor, a separate filter, if I just have the mono camera and I add my own red filter in front of it, I'm still going to have a higher efficiency of light collecting. So that's on top of the fact that you're already having less pixels gathering red light. It's also less efficient than the red camera. And then one quick thing I'll say while I'm here is, so you'll notice how for the mono, for the color once they cut it off, but you'll notice how it has wavelengths going all the way to 1,000, right? And there would be some more wavelengths here on the left side to 300, right? So if you even with an OSC, if you don't have any filter, you're going to be gathering light in this range as well, which is the UV light, and you might be gathering some light on this side of the light curve, which is the IR side, right? So gathering that light too can give you some bloated stars. So I would recommend, even if you're using an OSC camera and you don't want to do narrowband, at least putting a luminance filter, right, which is really a UV IR filter, which is really blocking anything beyond like 700 nanometers or less than 400 nanometers. So it's blocking the UV range and the IR range, and it'll give you better stars. All right. Any questions on cameras so far? All right, so now connecting, right? Let's say you pick your Astro camera and you want to connect it to your telescope, right? You have all these different adapters. How do you know how many adapters to use? What's the right adapter here to use? And then that will depend on your telescope, right? So every telescope will have something called a back focus distance, right? So that's the distance between the back of the telescope, right? The opening on the telescope on the back to your camera sensor, not the front of the camera, the actual sensor on the camera, right? So if I take my camera here, right? So this is the front of the camera. You'll notice that the sensor, right? There is some distance between the sensor and the front of the camera. Right? So you got to account for that as well. And so you need to make sure that your sensors have that correct back focus distance to be able to focus correctly, right? So that this diagram here, right, is showing you what the light's doing. It's going to come up and focus onto a point, and where that all the light rays meet up on that point, that's where you want your sensor to be. So again, every telescope will tell you what that distance is. The most common ones is 55 millimeters for historical reasons. But again, different telescopes will have different ones, like an SET, for example, like mine. The back focus is 146.1 millimeters. So you'll just have to see what your telescope is doing. Luckily, if you go to your camera's manufacturer website, they'll tell you, right? Most of them, again, 55 is the most common distance. So they'll tell you what to do to reach 55, right? Whether it's through adapters or through components and adapters, right? So you can see right here, it's telling you that the distance between the front of the camera and the sensor is 17.5 millimeters, right? So because I already have 17.5 millimeters, now I only need another 37.5 millimeters to reach 55. And I can get that 37.5 either by having two adapters, or I can have a filter wheel, which is 21 millimeters, and this adapter here that's 17.5 millimeters. And everything you'll notice is you'll see here when using the adapters, they're telling you 55. When using the filter wheel, they're telling us 56. So what this particular manufacturer assumes is that the filter, when you have light going through a filter, it's going to change. It's going to move your back focus by about a millimeter or so. So they take that into account by making their filter wheel slightly thicker, right? So the 21 versus the 20. But if you go, for example, on the CWO's website, they'll have the same type of diagrams. They'll even tell you, what size, which is M48, AM42, and the thread size and all that. So make sure to check the website for your camera if you have any questions on how to reach the right back focus. All right, so once you have your camera connected, you figure out what your back focus is, which, by the way, still that doesn't mean you don't need to focus your telescope. You still need to focus it. You just got to be at the right back focus distance to be able to focus. So once you do that, right, and you connect your camera to the computer, first thing you'll see is that you got to put in some settings for your camera to use it, right? You'll see something like gain in an offset before you can start taking pictures. So I'm going to cover what those are so you know what to set those to. So gain, really, it's an amplification of the incoming signal. So, right, it's taking the light, it has photons, right? When it hits the sensor, it converts the photons to electrons. So gain, all it's doing, it's amplifying those electrons. So a higher gain, right, because it's kind of increasing your signal, if you will, it's reducing your noise, right, and the amplification of that signal. So you might think, great, I'll just amp up the gain. But because it's increasing the gain, it's also reducing the dynamic range, right, which is the range of different brightness the sensors can record, right? So the range between bright and dark. So as you increase the gain, you're losing the range of bright and dark, right? That's why, like, if you go too high in gain, it's analogous to ISO in a DSLR mirrorless camera, right? So if you go too high in gain, you'll notice your picture starts getting brighter and brighter. It's because you're losing how much on the dark side you can have, right? So you're reducing that range. So you want to be careful what gain you pick. But then each sensor and then each manufacturer, depending on how they process that sensor, they'll have a different point again where the noise drops, and then you recover some dynamic range, right? So that's typically the good value you wanna shoot for. You may need to change it again from that point, depending on if it's a very bright target. But so, for example, here's the same sensor, IMX 571, right? That APS-C on CW and Player One. So I just went on their website and grabbed these images, right? So this is the CW 2600 and the Player One Poseidon camera, both again using the same sensor. So you'll notice that for both of these on the gain, so it's the bottom graph here is readout noise or noise versus gain. You'll notice that there's a sharp decrease here originally, then your gain is kind of steady, and then it just drops all of a sudden, right? And then it continues. So the drop for the CW is around 100. For the Player One, it's around 125 or so. And then you'll notice here on the top graph is your dynamic range. Your dynamic range is dropping as you are increasing the gain. But then when you have this sudden drop in noise, you have a slight increase in your dynamic range, right? So that's why this is a good value to shoot for, because you have low noise, right? Especially if you compare here. If I keep going down in gain, my gains and noise are minimal, and I'm losing a lot of dynamic range. So really, this is kind of the sweet spot where you want to be. But then again, if you're shooting a very bright target and you don't want to have to take like 1 second exposures, right? And you know you're going to take a lot of pictures anyways, where the noise is not as relevant because you're going to have so much integration time. You know, you could consider then upping your gain, right? So like for example here, if I go to a gain of 0, I'm going to have a similar dynamic range at a gain of 100. Yes, I have more noise, but now I can just take shorter exposures or keep my exposures longer, which again, if you that's less exposures over time, it kind of makes it easier to process. Or you might not blow out your stars, right? If you're noticing you're blowing out your stars because your target is too bright, you might then want to decrease your gain to see if you can combat that way. All right, so that's gain. Any questions so far on gain or cameras? Great. And then the other setting that you'll see on the computer when you connect your camera is the offset, right? So the offset, it's a small positive number that is added to each pixel to ensure that your camera never records negative values, right? So because you can't have negative brightness, but the noise that it's recording might cause the signal to dip. So if that happens, the camera will just record 0. So you might be losing some range there. So you want to set your offset to make sure that even when you have this noise causing you to go below 0, you actually don't hit 0. So to get what offset you want, you set whatever desired gain you want in your camera. You can take a short data exposure, and then you take a picture. You take your picture, right? Maybe a second with the lens cap on, and you check the minimum ADU in the histogram. And you want to make sure that you change the offset so you only have like 1 or 2 pixels that are at that minimum ADU, and that this minimum ADU is a value, not actually 0. So if you have 0, that means that you're for the ADU that means you're clipping some of your signal. And again, it'll vary for camera and manufacturer. So even for the same sensor here, for example, the Player One, I think the offset will vary anywhere from like 0 to 500, if I remember correctly, and for CW, it's like from 0 to 100. So you just have to play with it to make sure that it's correct for you. All right. So you have your camera connected to your telescope. You're able to point, and you took some pictures. and you're ready to stack them, right? So now the next thing you want to do is you want to calibrate your images. And again, I mentioned that this is being important in the necessary category because it'll really improve your signal, your pictures, right? So all images you'll need to calibrate to correct for camera imperfections or imperfections in your optical train, right? If things are slightly skewed, um, if you have dust somewhere on the lens or the sensor, you have hot pixels, right? Meaning you get a pixel, you'll notice sometimes that you may have noticed if you process your images, you'll have like a couple pixels that are solid red or green, right? That never change colors. You have some vignetting, so on the corners around the edges may start to get darker. So you need to take some specific types of images here to calibrate for all these imperfections. I feel like, especially lately, this has been debated a lot online. So I would say if you're going to take any sort of images, any sort of frames, calibration frame, make sure you're at the very least take flats, and definitely darks if you're not using an Astro camera. But the different types of calibration frames you want are biases. Those are extremely short exposure, so as close to zero as you can get it. And they are to cancel out the electronic noise, the baseline, right, kind of your image. Then you have the darks, which, as it implies, is just a frame with no light. So you put your lens cap on. You take these at the same exposure, time, gain, and offset, and sensor temperature as the light frames. So again, if you have an Astro camera, you may only do this once every couple months. And you do this to correct for thermal noise, right? So as the sensor is heating up, taking pictures, it has some noise. Any dark current, hot pixels, or amp glow if your camera has amp glow. And then you have finally the flats, which are basically an evenly illuminated frame that you use to correct for dust modes, vignetting, sensor shading. What you want to do here is once you have your evenly illuminated light, either by pointing to the sky with some white cloth on it or putting a dedicated flat panel, is you want to look at the histogram and make sure that your exposure length captures about a third of the histogram max value. So if you have a DSLR, you might be looking at the histogram on your screen and varying the exposure time. If you have an Astro camera and you're using a computer, all programs will have a kind of a flat automation where you'll tell it what percentage of the histogram you're shooting for, and it'll determine the length of the exposure that you need. Right, and then depending on the sensor you're using for your camera, if you require longer exposure on your flats, like a couple of seconds, you may need to take additional dark frames then at the same exposure that you're using for those flat frames, and that's what's known as dark flats. Not every sensor needs it, right? Sometimes the biases are enough to calibrate for that. So again, the flats, you can automate it with a flat panel will automatically close at the end and take the flats. You can buy a drawing pad on Amazon, put it on top of your telescope and tell your program right at your brightness level to figure out the exposure time. Or again, you can just point your telescope to the zenith early in the morning during twilight and diffuse the light with a white t-shirt and take some frames, right? So there are really complicated ways of doing it, really simple way of doing it, but the point is you should be doing this to get better images. Right. Questions on calibration frames? Right. And then very quickly, I'll touch upon this. You need an imaging computer, especially if you're using an Astro camera. So all your computer needs to be connected to a computer. If all of your equipment is CWO, I think maybe the mount doesn't have to be from CWO. An ASI Air is a pretty convenient solution, right? It's all plug and play. It's all from the same manufacturer. They know how everything behaves. it'll work out pretty nicely. Um, if all your equipment is from different manufacturers, or you just like to tinker around, alternative solutions are like Nina or SharpCap. Nina is free. It's just a program you download. It can run on any computer, whether it's a laptop or a mini computer. SharpCap, I think the pro version you have to pay like $18 a year. Um, and I should say there are a couple new kind of like plug and play ASIR type solutions that are coming out. I don't have any experience with either the ASIR or something else. Mostly use Nina on many computers. Um, the downside of something like this, right? The upside is you're in control of it. You can use whatever brand of equipment you want. Is now you have to go and figure out how to connect all the equipment yourself. There is some support online, or you can ask a club member or something if they've used it, but and you have to go and find the ASCII driver if you're using Nina, or if you're using some other thing called like Indie, you need to find the Indie driver. But you got to go on the website for the manufacturer of the equipment you're using, find the ASCII driver, download it, and then connect it to Nina yourself. Make sure it's working correctly. So if you don't like to tinker, or you don't want to bother downloading drivers or anything like that, then something like the ASIR and just buying CWO is a great solution. But if you don't mind the extra legwork, having your own setup with Nina is great, and is significantly more powerful. And I think at some point next year, maybe early next year, I'll do a course on Nina and how to set it up and how you can set up sequences. You go over that a little bit more. All right. So you have your camera, you have it connected, the proper back focus. You figure out what gain you want to use, what offset, and then one thing you have left to do before you start taking images is you got to actually focus your camera onto the stars. Right. So before you start any imaging session, you have to actually achieve proper focus. And what you want to do is you want the stars to look as small as possible and as round as possible with focus, right? So if you're doing your focusing manually, you can use something. Well, first of all, you can just simply try to do eyeball it and play around with the focuser, right, until you notice, oh no, that way they started looking they were looking small, and then they kept going, oh, they're looking big. So you back it out and you try to manually make it as small as possible. Another solution, if you're doing it manually, is to use a Batman mask, which looks like this, that you put in front of your telescope. And then when you look at a bright star, you'll notice this pattern, right? You'll notice like an X pattern through a light, and then a line going through your star. So the image on the center here is the one that's properly in focus. When you have the middle line going straight to the center through that X. If you notice here on the left, the line, this middle line is slightly to the left, and then here on the right, it's slightly to the right. So you gotta move the focuser to the right, and then here you would move it to the left. So you would do this, and if you don't have an electronic focuser, you may want to check your focus on a couple times throughout the night. Right, due to the temperature change at night, lighting changes, if there's a partial moon, atmospheric effects, right, like all the humidity will cause the light to diffract differently as it's changing. The sky temperature, all of that will cause your focus to change throughout the night. So your image may look great at the beginning. You go to bed, you don't do anything, you wake up in the morning, and you realize that towards the end of the night, they were looking like crap because your focus changed. So an electronic focuser is something you physically attach to your focus knob. And once you set it up on the computer, will automatically refocus the image as soon as you can set it however you want. You can set it to refocus if the temperature changes. You can set it to refocus every hour, every 10 minutes if you want. What I do is I set it to refocus when it notices an HFR increase by 10%. So that's a half flux radius, and um, I'll go over that here next. So the way the electronic focusers work is that they move first of all, you have to start near focus, right? And then you tell it how many steps to move out initially, so that it'll essentially defocus your image. It'll take a picture, and then it'll measure the HFR. So that's the half flux radius, and that is the radius of the star that contains half of the total light, like the flux, in pixels, right? So it's measuring the radius in pixels that have half of the total light of the star, right? And so you want to minimize that value. When you minimize that value, you know you're in focus, right? So the two things you have to do for the electronic focuser to work is you have to be near focus when you start, and then you have to then figure out how many steps you want it to move. So you only do this once, right? And then from then on, it'll do it automatically, right? So if I start right near here, it'll automatically defocus all the way here, and then it'll start taking pictures, right? And it'll start gathering data. It'll be on one side of the focus point, and then it'll move to the other side of the focus point. And then it fits a line. It fits this curve, this V-shaped curve, this parabolic shape. And then it can do some math, right? Once it has this line fitted through those points, it can do some math to figure out what focus step would be the one that gives you the minimum value of your HFR, right? So that you can see that would be this red dot here. And then that's how it knows that it's in focus. And then the other thing you need to define once, depending on the focuser you're using, is the backlash, which is the focus steps that it needs to take before the gears start moving, right? So it's to account for the slippage in the gears in there. This is all by trial and error, and again, you do that, and you do the step size that on the very first time the focuser is used. So I can go in more depth about that on Saturday in person if you need some help, or on a future class when we're talking about setting up your Astro computer. But any questions so far on that? All right, great. So moving on. All right, so once you're in focus, the other thing you want to set up during your imaging session that will help you a lot is dithering. So dithering is you're telling the mount to slightly shift the position it's pointing to between exposures. And what that does is that each image then, or every couple images, depending on how you set it up, will move the stars, will place all the stars on different pixels, right? So what that does is that every now image, or every couple, let's say every 3 images, which is typically what I set it to be, and the noise or any hot pixels and any bands you'll notice and any pattern noise will move around and won't always be in the same place. So because it's not always in the same place, now the second algorithm knows that that's not something that needs to be there, and it can easily average it out. So you want to set your dither frequency to be every couple frames, right? And you want to set it to dither between 10 to 20 pixels. So your frequency will depend on your exposure length, right? So if you're taking like 30-second exposures, maybe you don't want to set it to dither every image, because dithering takes time, right? So it has to move the mount, then make sure if you're guiding that the mount is stable, and resettle before you continue taking pictures. So all that adds up, and so the more you dither, the more time you're losing. So typically, I typically do 3-minute exposures, and I set there to dither every 3 frames. You know, if I'm doing like a luminance shot, I've noticed that But even if for shorter exposures, I might want to dither at a higher frequency to really cut out the bands and the walking noise. So now that brings up a good segue to the next, which is guiding. So like I said before, all mounts have tracking errors just due to mechanical imperfections in the gears, mechanical flexure in your imaging trains, load imbalances, right? Maybe your weights are not perfectly balanced. You're not going to be able to polar align it perfectly, especially every night. Again, as your atmosphere changes, it might deflect the light, so your object may appear to be at a different position. So if you want to take long exposures, right, for a couple minutes, you need to account for these errors. So you have to tell the mount how to move to account for that error, right? Because the mount will just think that it's tracking the same RA and declination, because again, those are not changing for your object. Right, so the mount itself thinks he's perfect and he's tracking it perfectly, but you need to take into account those errors and tell it how to correct for them, right? There are minute corrections, but they need to take place. So the way to do this, you need a separate camera, I guess a smaller camera that can keep track of a set of stars. And then when those stars move, you have a separate software, guiding software, that will tell the mount where to move to correct its position, so that the stars that it's tracking are the same place, right? So again, whether you need to guide depends on the mount you have and how long you plan to shoot, right? Like really expensive mounts, you can do 5 minutes of unguided and have no problems, right? Or maybe you have an EQ6 and you only have a red cat on it, so you may be able to get away unguided for like 2-minute exposures, 3 minutes. Harmonic mounts, though, just because of the setup they use and their gears, that they're known for not being able to go unguided. So you'll definitely need to guide for those. So those corrections take place while you're taking your exposures, right? So that's keeping those stars perfectly still in the same pixels during the long exposures. And I think setting up the guiding is a beast in and of itself. Sometimes, right? So you can do this here. Again, so you'll need a guide camera, right? The small sensitive camera with a small sensor that can capture a larger field of view of a star field every 1 to 3 seconds. Then you need a separate guide scope, a separate scope for that camera, or you need an off-axis guider, right? A guide scope is essentially a small refractor that you mount on top of your main scope, or you have an off-axis guider, which is part of your imaging train, and it's essentially a prism that's picking up light from the main scope's optical path and is deflecting it onto the guide camera, right? And that's part of the imaging training. Here, I'll show a picture in a second. And then lastly, you need guiding software, right? I think the most common one is PhD2, or stands for Push Your Dummy version 2, because they really try to make it as easy as possible. So what this is doing is it's tracking the centroid of a star, or in multiple cases, multiple stars, and it calculates how much that star drifts every second, every 2 seconds, and then it sends a correction to the mount to account for that drift. Or if you're using an ASIR, right, the ASIR will have a guiding feature, and really what's under the hood of the ASIR guiding is PhD2. So if you're setting it up yourself, you have to set up PhD2 yourself, which can be painful, right? Knowing how to squeeze performance out of it. And I'll give some guidelines here in a second. Well, the first of all is, how do you pick the guide scope and the guide camera? So the rule of thumb is you want the guide scale to be
similar or up to 4 times larger than your main imaging scale. So imaging scale here is defined by this equation, right? So 206 times the pixel size in micrometers divided by your focal length in millimeters, right? So important to use the right units here for those. If some of you have a science background, you might want to say, well, I want these to be the same units. No, you want to keep them in micrometers and millimeters because this factor here will account for the unit conversion. So you, for example, a red cat with IMX 571 sensor that has a pixel size of 3.76 micrometers and a focal length of 250 millimeters, I'll have an image scale of 3.1 arc seconds per pixel. So when I'm choosing my guide scope, guide camera combination, I want to make sure that I don't exceed 4 times this value, right? That's kind of like the rule of thumb. And so a very common guiding setup for the Red Cat is to use from the same manufacturer, William Upkiss, this Uniguide scope that has a focal length of 120 millimeters, and ASI camera, the ASI 120 mm Mini, that has pixel size, basically the same size as the IMX 571. And that gives me an image scale of 6.46 arc seconds per pixel. So basically double my main imaging scale. So I know that this is a good setup to guide. And this is pretty much the setup I have on my Red Cat, and it works really well. Now, if you, so guide scopes work really well with refractors, right? And for shorter, medium focal lengths, if you're moving up in focal lengths using a Newtonian or an SCT, as shown here, you want to get an OAG, an off-axis guider. That will work much better with these long focal lengths. Like I said, it's part of your imaging train. So here's a random picture of the internet I found. Right, so part of your imaging train where the camera is at the top. You see here it has this prism. So if the light's coming from the telescope, right, it's going through here into your camera. A little bit of that light is hitting the prism and deflecting upwards onto your guide camera. So now your guiding focal length is the same as your imaging focal length, right? OAGs, especially at long focal lengths, have their own set of problems because sometimes you may not find a guide star. You got to make sure the prism is large enough to capture as much light as you can. So they have their own set of complications, but again, if you're going already through the pain of using an ST, then you need an OAG to be able to guide better. Right, so since it's part of your imaging train, you're gonna take its thickness into account into your back focus. Other thing to keep in mind, if you're using a filter, to place the filter wheel or any filters behind the OAG, because you don't want your light to go through a filter and then through your guide camera, because it'll make it harder to guide. And another reason to take flats is this prism, you can move it up and down, right, to try to get near the sensor or capture more light. Depending on where you put it, it may actually cast a shadow onto your sensor. So you'll want flat frames to make sure that it can correct for that shadow into your sensor. Which brings a point that I forgot to mention during flat frames is that not only do you want to make sure you take them at the same settings, but at the same rotation, right? So if you rotate your camera for different targets, you want to make sure you capture flat frames at every rotation as well. All right, so back to here. In the guide camera, it only needs to measure the centroid of the star, right? So the center of that star. They don't have to be sharp images, right? You don't want pinpoint stars. And actually, it kind of works better if that's slightly out of focus to better calculate a centroid. So you don't actually need to block the UV and the IR light from your incoming light here. to guide, right? So I know some manufacturers will try to sell you an UV IR filter for your guide camera, but you actually don't want that. It'll work slightly better if you don't block that light. All right, guiding performance, right? Because that, like I said, that can be a pain. So you want your guiding performance to be smaller than your image scale, right? So for something like my Red Cat 51, I'm not gonna try to stress to get like 0.5 arc seconds of guiding performance because my image scale won't notice that. So don't fret on what RMS, right, or root mean square value you're getting. It depends on your focal or your imaging scale. And then the guiding algorithm, if you go on PhD2, and again, this is something to go more in depth on a future session. What guiding algorithm you want to pick is depending on the mount and how much payload you're using. So, for now, I'll say just research your setup, see whether people recommend or what's out there. That might give you some idea. Good guiding performance is based on having good polar alignment. So if you want good guiding, just make sure you really nail that polar alignment in the middle at the beginning of the night, and then you have a good guiding calibration, right? You need to calibrate your mount to the PhD2 so it knows what drift to expect. So PhD2, I'm not sure what the ASIR does for guiding, but I know in PhD2 there's a guiding calibration assistant where it will point your scope to the optimal location in the sky for calibration. So I've noticed a big improvement by using the calibration assistant to get a good calibration. And then it has a guiding assistant as well. So once you have a good calibration, you can use the guiding assistant. So essentially what it does is it doesn't guide for a couple minutes, and then it analyzes the performance during those few minutes, and it gives you some improvement and recommendations for your guide settings to get better. So definitely use these two, and I've noticed a huge improvement, especially by using calibrating the location that it's optimal, right? Which is really the optimal place to calibrate is as close as you can get to a declination of 0 and near the meridian. So again, the calibration assistant will kind of automatically point your scope to that and give you good calibration. All right, last thing I wanna touch on tonight, and kind of talked about earlier, is filters. So again, if you're using a mono camera, you will need some filters, right? Whether it's RGB, LRGB, or SHO filters, right? There's no such thing as light pollution filters when using a mono camera. Typically, those are referred to as the narrowband filters, which are already here. You also need a convenient way to hold the filters, right? Whether it's a filter drawer, which is manually, which is great if you really don't think you're going to use different filters throughout the night, then a filter drawer is perfect, right? Because you set the filter at the beginning and then it stays there all night. But if you want to use different targets, maybe with different filters, or you do want to change filters throughout the night, right? Especially to account for the moon position and all that. Having an automated filter wheel is great. Depending on the size, you can hold anywhere from 5 to 8 filters. And then as far as filters, they come in different sizes as well. So you gotta make sure that you get the right size filter for your sensor size, right? Don't get a 1.25 inch size filter for a full frame sensor, right? You're gonna block a lot of light. But filters can be either unmounted, which is just bare glass as shown here, that you would put directly on the filter wheel, and then they give you, do I have one on here? These little tabs that you screw on top of it to hold the filter in place, or mounted filters that are shown here that kind of have this metal border around them with some threads that you would just thread in directly to the filter drawer of the filter wheel. So filters and focusing, right? Because if the filters create slight changes to your back focus. So every time you change filter, you want to refocus, right? Whether it's manually with a backlight mask or with your autofocuser. But that's time consuming, right? So an autofocus routine can be a couple minutes. So if you're changing filters often, that's a lot of time you're losing. So alternatively, what you can do is determine what your focus offset is. So you do a series of autofocuses routines for every filter in one night, right? So let's say you anywhere from 3 to 5 sets. Then you pick one filter that's going to be your focusing filter, typically the luminance, because since it has such a wide range in wavelength of light, um, you can you don't need as much time per focus point, right? It can just be like 2 to 5 seconds, so you can go through a full focus routine pretty quickly. And then you calculate the difference in average focus position between the luminance filter and the rest of the filters. And that becomes your filter offset. So when you change filters, now, so let's say I go from red to blue filter, um, all I have to do is change the focuser position based on the offset. I don't have to actually refocus again, because I already know what the offset is between each filter. Um, and again, something like Nina, and I'm not sure, but I'm sure the ASIR will do it, have routines to automatically go through this exercise and calculate what the filter offset is for you. But if you need to do it manually, here's how you would do it. Um, so this is nice because then you know what, based on your current focus point, where you would need to move when you change filters to remain in focus. So it saves you some time. Another thing when you're considering filters is you want to decide between LRGB versus narrowband, right? So what I have here in this graph is the wavelength, the band that each filter is taking, right? So blue again is between 400 and 500, more or less. Green between 5 and 6, red between 6 and 7, right? And then you get your luminance filter, which is really the whole spectrum between like 400 and 700 that you would use to get some detail, right? So again, if you're using a one-shot color camera, you're taking RGB simultaneously. You're just doing it on a lower efficiency, like we were discussed. And then there's narrowband. When you're focusing on specific wavelengths that a nebula might be emitting, right? So you have your sulfur 2, right, which is basically once ionized sulfur, which has a wavelength of 671. H alpha, hydrogen alpha, which is the most abundant gas out there, has a wavelength of 671, which again is in the red filter, right? So when you're using a narrowband filter on a one-shot color camera, right, only the red pixels in that camera can capture HA. So your green pixels here are not doing anything, and your blue filters are not doing anything for HA. And then you have O3, which is 500. So for one-shot color cameras, you'll notice that the filters won't be HaO2, right? So you'll capture a little bit of O2. And then for narrowband, what you'll do is you'll capture light with these filters, and then you map these frequencies to some RGB combination, or in any combination you want, I guess, per channel to get a color image. Okay. So a little bit of narrowband and OSC, like I mentioned before. So these narrowband filters for one-shot color cameras, they isolate the HA, the O2 frequencies, so you can capture these simultaneously. All right. So this is the popular Optimum L Extreme filter, and it's showing you that it's only capturing light at the O3 wavelength, right around 500, and the HA wavelength around 656, right? And it's showing you that, right? So these are the Na, the sodium wavelengths, and Hg, which is the mercury wavelengths. And they're showing you those because street lights used to be sodium and and mercury, right? So if you were blocking those wavelengths or not capturing the wavelengths, you're avoiding a lot of light pollution. So they're blocking light pollution by simply reducing the available wavelengths. But again, due to the quantum efficiency matrix we talked about, it's kind of a inefficient way. But again, because hydrogen alpha is so abundant, when you use these filters, you'll really you'll get a really good image because most of what's out there is red. So it can be worthwhile if you're using an OSC. And the reason why nowadays, using trying to block these emissions might not necessarily matter much. Nowadays, most lights are LEDs, and LEDs really cover the entire spectrum between 400 and 700. So blocking, trying to block the mercury and sodium is really not doing much because most city lights nowadays are LEDs anyways. Here's another filter, the SV260, again, a light pollution filter, which again, you can see what they're doing is they're telling you this green is these constellation emission lines, right? Like HA and O2 and H beta is 2. And they try to block around the yellow, which they call the artificial emission lines, which again, it's the sodium, mercury, which depending on what city you live in, but especially for us, I think most cities, most streetlights in the Orlando greater area these days are LEDs. So trying to just block these out really doesn't do much because you still have a lot of LED light that's coming through in the other wavelengths. All right, that's really it for tonight. Like I said, in-person help plan is to get to Geneva a couple hours early during the daylight. So if you have some specific questions, plan to get in before sunset to go over your imaging setup or try to go over anything in person if you want. And I'll open it up if there are any questions here online over anything I talked about.
All right. So there are no questions, and thank you everybody for tuning in, and I hope to see you all on Saturday. Thank you.
Thank you.